let's skip reviews and just go to the place where we left off. So we need to build total density of all electrons, because by theorems total density gives energy, and we are having a procedure how to go into artificial world of Kohn and Sham where electrons do not interact with each other. And in this artificial world, we build one electron orbitals. And the only thing is to return back to multi-electron problem by combining this one electron orbitals in some way. In the past, when we were studying Hartree-Fock theory, we were taking one electron molecular orbitals, taking Slater determinant, and making multi-electron wave function. We are going to do something better than that. But this concept can be used as an abstract reference point. I do have yes, and we have just two goals for today. We find total density based on these Kohn-Sham orbitals, and then setting the flowchart loop. And I have this derivation and this equation in typed form, so I do not want to make you to read my ugly handwriting. So in one electron quantum mechanics, if you have only one electron, only one orbital, then by making a product of conjugated orbital and orbital itself, one is getting probability distribution or density. Right? Now, if we have multi-electron wave function that depends on so many electrons, what if we take absolute value squared? It is logical to assume that it will be probability distribution or density which depends on many multiple electrons. This will be reasonable, it will be correct, but very unpractical. It still will be function of number of electrons times 3. And then we'll lose all benefits of DFT. But here is a procedure. For density function theory procedure, we never requested, we never told that we need multi-electron density. The concept used in theorems was density of all electrons in a single point. So we need to project this multi-electron density that depends on R1, R2, and so forth, onto only one coordinate. So we need one electron density. And this can be achieved by performing integration of all Cartesian positions, or all positions of atoms, except position of not atoms, electrons, of electron number 1. So we skip number 1 and then perform integration over position of electron 2, position of electron 3, position of last electron. So if I would add dr1 here, then the result, and one more integral, then the result will be equal number of electrons. But if I do not do it, if I do not do last integration, I am obtaining function of R1. I'm obtaining density of all electrons evaluated at position 1. So I'm going to practice this idea, but for simplified case, when we have only 2 electrons and 2 orbitals. So I will literally write a Slater determinant of 2 orbitals, orbital 1, orbital 2, for electron 1, electron 2, and then literally compose density of 2 electrons, R1, R2, and then literally integrated of everything except R1, which will be integral about R2. And as a result, I will obtain density of all electrons evaluated at position of the first electron. So by performing this simple operation, we will see some trends that can be extrapolated from 2 electrons to any number of electrons. Because the trends, the answer will be very, very simple. So, and very natural. You can even guess what will be the answer. And if someone wants to speak, please raise hand and tell. It's not mandatory, only if you already know the answer. Okay, there will be a chance to speak later. I do not like my handwriting. Let me find the thing which is better typed. Okay. So in next years, it would be better to derive it in front of class. But here, since we squeeze information, I'll just speed up. So how do we perform Slater determinants? Okay. Would you teach me how to take Slater determinants?
Sorry, Professor?
How to take Slater determinants? How to take determinants of matrix 2 by 2?
Means how can you get that line?
Yes.
The
Yes.
yeah, just multiply with, if that one consists of a and a with d. Yep.
So diagonal
Yeah.
multiple of diagonal.
Mm-hmm.
Right?
Yep.
Okay. So we do have diagonal theta 1 r1, theta 2 r2, right? Minus off diagonal.
Yeah.
So theta 2 r1, theta 1 r2. So we have Slater determinant multi-electron wave function.
Yes.
Now, if we put a little star here, it means we just put star in front of each orbital, right?
Yep.
Okay.
Same
And
thing.
now here I'm trying to implement the my own prescription. So I'm taking density of R1, R2, and integrating over R2, which should be density of all electrons at point R1. And for this density, I just multiply wave function, multi-electron wave function, by wave function conjugated. Make sense? Density. So what do I or what do you expect if I plug in this wave function here, this wave function there? So each wave function is a summation of two terms, right? So we'll have brackets, each of which has two terms. How many terms will be after we open the bracket? What?
16, I don't know.
If it is not clear, okay. So this one, psi without star and psi with star, it will be like if we call this pair as A, B, then here we will have A star minus B times B star times A minus B. So there are two terms in first bracket and two terms in second bracket. If we open brackets, how many terms will be?
3.
If we take similar things, we can get 3, but generally it should be 4, right? Do you see it? Well, would you agree about 4?
Yes.
Okay, yeah, so we'll be like A star A and so forth, right? So here we do have this diagonal minus subdiagonal, diagonal minus subdiagonal. Here are our two-way functions, and if we open brackets, there will be 4 terms. So at this point, it can be a little scary and ugly. So diagonal times diagonal. And in the last one, no. Then when indices here and there of the orbital and electron coincide, it is diagonal. When they do not coincide, it is off diagonal. So we have another instance when they are coinciding. Here, there, and we have instance where they coincide here and there. And everywhere else, there are terms originating from off-diagonal terms. So off-diagonal, 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 off-diagonal. Is it clear where this equation came from? I know it is big and scary, but let me know if you prefer some additional comments. Is it okay, not okay, or more or less? Okay, so we just multiply things. And now, after we perform this multiplication, we need to integrate over R1 everywhere where it happens. So while performing this integration, I'm going to use the orthogonality property. So if I have theta 1 times theta 1 star, and they depend on the same argument, like R1, 1, D R1. What will be the result?
1.
Correct. What if we integrate orbitals with different indices, like 2, star. We need to put 2 here because we integrate over R2. Theta 2 R2. Yeah, thank you to those who answered in the chat line. Theta 1 R2 D R2. So this one will be 0, right? So if the indices of the orbitals do not coincide, it is 0. If they do coincide, it is 1. Okay? So now I'm going to inspect this long equation for availability to practice this orthogonality property. And notice, there are no approximations, there are no cheating. So we openly just take Slater determinant, multiply 2 Slater determinants, and integrate. So this procedure is absolutely precise. There are no approximations at this stage. So we have R2 here and there. So it uses these 2 yellow things depend on R2 and integrate over orbital number 2. So if you perform integration only in the first line, the integration of this and that together will give 1, right? So from the, if we process the first line, it will be converted into product of remaining things. Theta 1 star R1, theta 1 R1. So here we got rid of R2. Now let's continue. In the second line, I have R2 here and R2 there. So the indices of theta of this wave functions are different, right? So what will be the result of integration in the second line?
0.
0, which means the whole line will be 0, right? We don't care what will be the other factors. If at least one factor is 0, we don't care about the rest, right? Now let's go to the next. Here is variable R2, here is variable R2, and we have this theta of 2 and theta of 1. So the numbers of orbitals are also different here, 2 and 1. So integration over these 2 orbitals will be equal to what?
0.
Yes, thank you. So the result will be 0. So we already get substantial simplification. We get rid of 2 lines, 2 terms in this long equation. And let's do the last line. So we have variable R2 here and there. And we have product of theta star and theta with index 1. So if we integrate over these 2 terms, the result will be
1.
Then out of this term, we will keep only these factors. So theta star 2 of R1 multiplied theta without star 2 of R1. So out of the whole long equation, we got only these two things, and they have plus sign between them. So it is something very complicated that even not possible to analyze. But as a result, we got summation of two simple things, which are first orbital star without star at point 1 R1, and second orbital star without star at point 1. So some people consider this result very beautiful. Function, we already covered it. And the product of one electron orbital, 1 R1, with star and without star, can be R1, can be interpreted as density contributed from the first electron, or we can write it down as θ1 absolute value squared evaluated at 0.1. And second term will be a density of second orbital absolute value squared evaluated at 0.1. Yes, no, or more comments are needed. Let me know if anyone needs more comments.
I need more comments. How did we go from the result from the last slide to this formula in this result?
Okay.
I'm wondering where the square is coming from, basically.
Okay. Yeah. It's a legitimate question. Thank you. So here we got density of all electrons evaluated at 0.1 equals to, so through our integration, we removed a lot through orthogonality property. We removed a lot of terms. We removed the two lines. We completely removed them, and so these lines were removed. And from the first and last line, we did remove those that were already used for orthogonality property. So we left only these blue things, θ1 R1, θ1 R1, θ2 R1, θ2 R1. And this expression, I don't have more space, but this one is the same as θ1 absolute value squared, and this one is the same as θ2 absolute value squared. So the only thing that we didn't discuss was that the orbital with star and without star is equal to the same orbital absolute value squared. Is there a necessity to explain this statement? If yes, I'm ready. It's quite quick.
Yeah.
Okay. So the wave functions most typically look like they are proportional to exponential minus I, should be here like P h bar x. So something with imaginary unit. Then theta star, star means flip the sign by exponential, plus I P x divided by h bar. And if one multiplies these two things, with star and without star, then one is getting product of these exponentials, and product of exponentials means summation of their powers, which will be plus I px over h minus I px over h, which will be e to the power 0, which will be 1. So the multiplication by complex conjugate is equivalent to absolute value squared. And wave functions are already normalized, the absolute value square is 1. This is an example for wave functions, and another example that I will not go over in details. If one takes like numbers, not functions, a plus ib times a minus ib, and evaluates it, one will obtain an additional proof for the statement. So multiplying complex number times its conjugate gives absolute value of this a square plus b square of this complex number. Is it better or still insufficient?
Better.
Okay, yeah, thank you. Okay. So here is our result. And if you go from 2 electrons to n electrons, then we, instead of putting sign plus here, we put symbol sigma. Instead of counting literally, not here, counting orbitals like first, second, we can call it orbital number I, and we can make summation over all orbitals with index I. So it is summation between terms. It is equivalent, is symbolized by this Greek sigma. So the first goal of today's class is done. If we solve one electron Kohn-Sham equations in this artificial universe, and we get Kohn-Sham orbitals, we can add their absolute value squared together of all occupied electrons, for all occupied orbitals, and get total density of all electrons. So this is exactly the object that we were talking about in theorems. So DFT theorems speak about this object, density of all electrons. And there are ways for total energy. There are equations that I will try to cover on the next lecture, how the total energy is obtained out of total density. So these equations, how the energy is obtained of density, are similar to what we considered about 4 lectures ago in Thomas Fermi theory. You probably remember integral of density 5/3 dr. gives total energy if there are no ions and there is no electron-electron interaction. In real life, this equation will be a little more complicated, but such equations do exist, equations that convert density into the energy. Okay, so and now we are coming to the second goal of today's meeting. Do not believe this. It's not yet ended. Yes, here. So by now we do know all theorems and all practical equations that are sufficient to write a computer code analogous to Gaussian or WASP to practice density functional theory and find electronic structure of molecules. So if you hate equations, here is the list of main equations. And before I give them, so we need the equation for total energy, right? So we just how the total energy depends on density. And we put rectangular brackets. We need potential. Potential, it is the thing that we plug into one electron orbital, and it is a functional derivative. So delta over delta rho, and here we subtract this total energy minus kinetic energy. So this is quick analytical formula that is quick if we do it as in Thomas Fermi. It is a little more advanced in practical calculations, but it relates to so-called exchange correlation functional that one selects in the drop-down menu of Gaussian. And there are also special commands to modify INCAR to use different functions in WASP. So this potential is something that we can use in the one electronic equation for orbitals. So for orbitals, we have kinetic energy, which is second derivative over position. And in front, we put minus Planck constant to masses. So that originates just from definition of quantum momentum. So this was kinetic energy plus potential. And this one electron Hamiltonian is applied to unknown one orbital function and generates energy of the orbital and allows to find orbital itself. So this is the equation that we were practically analyzing in the labs. So when we were doing density of states, we were using these energies. So these energies of orbitals were used for density of states. When you were plotting orbitals, you were taking absolute value square of these orbitals. This is part charge files. Okay, and the last equation we need to approach the glory of Walter Kohn and John Pople, who got Nobel Prize for DFT, is to connect previous three equations by constructing the total density out of these orbitals. And it is basically what we did in the first part of the lecture. So density in point R is equal to summation of all orbitals starting from first to number of electrons, and here we take orbital number I in point R, and we take absolute value squared. And this absolute value squared of orbitals, this is literally the content of the ParCharge files that you were putting. ParCharge. So, any questions about these equations? Do you want me to give more details? Like yes, no, or not sure? Okay. Lina is okay. Vova or Boston is okay. Vova, is it reasonable or you need more comments?
It's reasonable.
Okay, thank you. So Kia typed in the chat line. Sarah? I will. So there is a confident yes, and there is a not confident yes.
At first, I wanted to say more or less, and then when I think, I said just maybe yes.
Yeah, we design new gesture. Yes, not
Yeah, I was not sure.
okay, that's fine. That's fine. Thank you. So when you will do reports for the mini project, please consider to type these 4 equations in Microsoft Word and use them in explanation what is being typed, because everything we do depends on these quantities. It explains the methodology. And if in your future life you will need to include some calculations in your thesis or paper, this would be reasonable. And for the rest of today's meeting, and thank you for investing your time. I understand that I'm going over time, but it's an important part that we will complete quite quick. We need to connect this equation together. And here are the words why it is needed. Similarly to the Hartree-Fock theory, we are mapping. We're doing a map of multi-electron problem onto one electron solution. So in the actual things that we are solving, we will operate only with things that depend on one Cartesian coordinate. So this map is quite an approximation and is quite a mathematical trick. And therefore, equations for such mapping are typically non-linear, and they cannot be solved only by diagonalizing the matrix. And the standard way to solve such non-linear problems are through self-consistent loops, which means we guess solution, we plug it into these equations, and then outcome of the previous step serves as an input for the next step. So we need to loop these equations together. And it is what we are going to do. So the density, I already typed this equation years ago, wrote. So we take the density from the last step and plug it into expression of total energy. And then total energy is used for potential. Potential is used to generate orbitals, and orbitals are used to generate density. And then we repeat it again. So here are the equations typed a little bit better. And we will convert this flow of the data into language of flowchart. So input and output are these cylinders, mathematical operations are triangles, flow of data are arrows, and condition is diamond. So conditions are needed because you remember this anecdote I'm telling every year about the programmer in the bathtub with a shampoo. Apply to head, rinse, repeat. So we need to break the procedure if it goes too far. So if the total energy computed at previous step and next step becomes smaller than some predefined tolerance limit, then we need to stop the procedure. So now I'm inviting everyone to go to the link, and I will ask you to fill. I know that some of you filled it and sent to me as an email, but I will ask you to fill elements of this quiz. No, not this. Yeah, this one. Who was? Tell me the names. I do not know who is doing that. So
I already did. Me.
no. I saw that you sent an email, but let's do now collectively. So who put the input into the first
Me.
book?
Input and density. Me. I did it.
Okay. Yeah. Thank you. Now, who was putting the
Me.
potential?
Me.
Sarah.
Shall with me.
Let's probably temporarily remove it because it will fit to different block better. Okay, who put it who placed the tolerance limit?
I did.
Who? Lola?
Lola, yes.
Okay, yeah, thank you. Yeah, the tolerance limit for the diamond, yes, correct. Does anyone wants to do another easy thing and place output? Output will be the easiest. We do not have total energy. I need to add another box, but it's fine. And probably this potential as Sarah placed it here is okay. Now, I think everyone did something except Boston. So Boston, you have 25% chance of success if you do it randomly. Oh, 50. So what goes first? Orbitals or density? Okay, orbitals goes first.
Hello, can you hear me?
Hello? Yes, yes.
Oh, okay. Yeah, sorry.
So you placed shown a conform equation in the middle. Okay. Anyone wants to move the last box?
Yeah, I cannot just edit the file.
Can do that.
Just move it in the last equation to the last empty box.
Yeah, but for me, I cannot keep that. Okay, I can do that now.
Very good. So, congratulations. From now on, you are certified expert in density functional theory. You know how it works, right? So, and when VASP is working within one electronic step, you see several iterations, and it gives energy at each step. So it goes through this iteration until the energy becomes acceptable. So back to and now it is time to refresh our memories and think about our fourth week when we pretended that each of us is a little computer, when we discussed geometry optimization. Remember, we were looking to optimize position of the ions until the energy, total energy as function of position, finds its minimum. Please give me a sign if you remember this, if you don't remember, or if you are a little bit. So Sarah remembers, yes, confidently. Lola, not sure. K? Not sure. Okay. I think we had a homework when we looked for minimum of the harmonic potential. We filled the table. Do you remember it? Then goes back and finds minimum. Do you remember this task? Okay, so we were following the algorithm. We were at each step we were looking for increment of position based on second Newton's law, like acceleration, which is gradient of the potential over position times time increment. So we were incrementing position, computing total energy, and checking whether it became less or more favorable than the previous one. Okay. Now we in the last lab and in the projects, we will need to practice either molecular dynamics or optimization of both, which means change position of ions, right? But when we discussed this optimization and change position of ions in the previous in the lecture 8 at the beginning, we thought that the total energy as function of position is something that we don't care about. We don't know where it comes. It's just a predetermined function. But now we do have density function theory. We have a code that for each set of atomic positions gives us total energy. So I'm going to do a crazy thing. I'm going to combine these two flowcharts. I'm going to use the flowchart that you just filled in this Google Doc document. I will fill this big flowchart inside this black box. So black box. Before we didn't know what it is. Now we know that we need a procedure to find the total energy. And I can copy paste the procedure that we have collectively set up inside this box. So now, from now on, you have complete plan, flow chart of WASP code or Gaussian code, how to do both electronic structure, geometry optimization, and molecular dynamics. And you see, there are two global cycles. One internal cycle, they are iterations for electronic improvement, for improving of electronic structure. And there is a external cycle for improving positions of ions, right? If one looks into outcar or OSICAR file, one can, or if one launches Gaussian in the command line, one can see how the steps are going through. The number, to stop it a little bit earlier, can be set up in the in-car. So this number of ionic steps is NSW. So if you set it to be 0, means we do not optimize geometry. If you set it to like 10, 100, 1,000, it means we either optimize geometry or run molecular dynamics. The number of electronic steps is keyword number of electronic modifications, and by definition is set to 60. So if system is not optimized in 60 steps, it uses what we got by now. But if you want higher precision, you can increase. If you want quicker calculation, you can decrease these numbers and be masters of your WASP calculations. So the file OSICAR shows how we go through the steps. So you probably saw this Davis algorithm. At the end of each electronic optimization, you get total energy. Then you go to next ionic step, and at next ionic step, one goes through electronic optimization once again. And number of electronic steps can be shorter than 60 if the system is well defined and converges well. And as we go from one ionic step to another, you see this energy is changing and getting smaller and smaller and smaller. So if we run for optimization, or it can oscillate if we look for molecular dynamics. So we achieved all information from the chapter into algorithm, except explicit equation for total energy, which will be the subject of the next lecture. So now we understand how the code works. You can operate codes efficiently, understand errors, and in fact, if you like programming based on this information, you can do a new DFT code. Maybe it is not needed for community because there are several codes, but this information is sufficient to program DFT. Okay. Thank you much for investing your time. Meeting is done. Everyone is welcome to disconnect and depart the room. And